Welcome to the Deep Dive. We're the show that helps you cut through the noise, get the key info, and, well, get you well-informed fast.
Glad to be here.
Today we're diving into maybe an overlooked corner of math, but one full of surprises. The Online Encyclopedia of Integer Sequences. You know, the OEIS.
Ah, yes, a fascinating resource. It's like a library where every sequence tells a story.
Exactly. And sometimes the simplest rules create these incredible patterns.
Yeah.
Our focus today is one specific sequence, A000265. Now, the description sounds, well, almost too simple. It says, remove all factors of 2 from n. Or you might see it as the largest odd divisor of n, or even just the odd part of n.
Right, deceptively simple phrasing.
It really is. So could you maybe break that down for us? What does it actually mean to remove all factors of 2?
Sure, it's quite intuitive, really. Let's take a number, say 12.
Okay, 12.
To remove factors of 2, you just keep dividing by 2 until you can't anymore, until you hit an odd number. So 12 divided by 2 is 6.
Right.
6 divided by 2 is 3.
And 3 is odd.
Exactly, so you stop. The result for 12, the odd part, is 3. Now, if you start with an odd number, like, say, 7,
Yeah.
well, there are no factors of 2 to remove in the first place, so it just stays 7. It isolates that core odd component of any integer.
Got it. That makes perfect sense. So let's look at the sequence itself then. The first few terms of O000265 go like this: 1, 1, 3, 1, 5, 3, 7, 1, 9, 5, 11, 3, 13, 7, 15, 1. I mean, looking at that, it just seems like a jumble of numbers, doesn't it?
It can certainly appear that way at first glance, but there is a deep order hidden in there.
Okay.
And one small but crucial detail from the OEIS entry: the sequence offset is 1.
Offset 1, meaning A1 is the first term we listed.
Precisely. A1 is 1. That's important for, correct indexing when we talk about its properties in number theory. It keeps everything aligned.
Right, good point. So our mission today really is to get under the hood of A0000C65. We want to understand its fundamental nature, explore some of these surprising structures people have found.
Absolutely.
And figure out why this operation, just finding the largest odd divisor, why it's actually so significant in different parts of math. Think of this as your quick guide to getting, properly informed about the odd part of n.
Okay, so to really dig in, let's formalize that core idea slightly. Every positive integer n, as you know, has a unique prime factorization.
Right.
From that, we can always write n in a unique way as n equals k2j. Here, k has to be an odd number, and j is just some non-negative integer power of 2.
Okay, k2j.
The sequence A000265 n is simply that k. It's the odd bit left over after you factored out all the 2's.
Ah, okay, so it's isolating the k.
Exactly. Let's run through those first few terms again with this k2j idea.
Good idea.
For A1, well, 1 is just 120. So K1, A1 is 1.
Makes sense.
For A2, that's 121. So K is 1 again. A2 quar 3, 3 is 320. K is 3, so A3. For A4, 4 is 122. K is 1, so A4, 1.
I see the pattern. What about, say, A6?
Good one. 6 is 321, so K3, A6 equals 3.
And A10?
10 is 521, so K10 equals 5. It always pulls out that largest odd factor.
That's very clear now.
And what's really neat here is that while A000265 gives you the K, the odd part, there's actually another sequence, A07814, that gives you the J.
Oh, the power of 2.
Exactly. It tells you how many factors of 2 were removed. It's like every number has these 2 components. Its odd essence, K, and its 2ness, J.
Huh, like coordinates.
Kind of. And this simple decomposition, this K2J idea, it seems basic, but it leads to some, really profound properties.
It's still kind of hard to imagine how just taking out the 2's leads to complexity. But you mentioned surprising properties. Like I saw a note from Carrie Mitchell calling it fractal.
Yes, that's one of the most striking things about it.
Fractal? How can a sequence of numbers be fractal? That sounds like geometry.
It does, doesn't it? But here's the idea. It's quite elegant if you look only at the terms with odd indices.
So A1, A3, A5, A7, and so on.
Exactly. What sequence do you get? You get 1, 3, 5, 7, 9, 11.
Just the odd numbers.
Precisely. The odd natural numbers. Okay, interesting enough. But here's the kicker, the really interesting part. If you remove those odd indexed terms from the original sequence, A000265.
So you're left with A2, A4, A6.
Yes. What you're left with is the original sequence, A000265, all over again.
Wait, really? The exact same sequence.
Essentially, yes, it reappears within itself. It's a form of self-similarity. That's the fractal-like nature Mitchell was talking about.
Wow. Okay, that is surprising. The sequence contains itself.
It's quite remarkable. It suggests this deep recursive structure baked right into the definition.
And how did people even spot that? That's amazing. But the structural surprises don't stop there, right? I read about a tabular arrangement, too, from Marko Matosik and Alexander Povolotsky.
That's right. Another way to see the underlying order. They described arranging it in rows.
Okay.
The idea is that every new row is the previous row interspaced with the continuation of the odd numbers.
Okay, walk me through that.
So row 1 is just 1.
Simple enough. Row 2 takes row 1, which is just 1, and interspaces the next odd number, 3. So you get 1, 3, 1.
Ah, I see. You put the 3 in the middle.
Exactly. Now for row 3, you take row 2, 1, 3, 1, and interspace the next sequence of odd numbers, which are 5 and 7.
So 1, then 5, then 3, then 7, then 1.
Precisely. 1, 5, 3, 7, 1.
Okay, I get it. And row 4 would use 9, 11, 13, 15.
You got it. 1, 9, 5, 11, 3, 13, 7, 15, 1. It builds the sequence in this layered, recursive way.
That's a neat visualization. What about the comment from Povolotsky about the ones at the ends?
Right. He noted that sometimes in drawings, those leading and trailing ones might be considered fictitious or added just for symmetry. But the core generation process, filling in the gaps with odd numbers, that defines the structure.
Fascinating. And there was yet another structure mentioned. Paul Kurtz saw it as a truncated triangle.
Yes, another geometric perspective. And what's significant there is that the columns and diagonals of that particular arrangement connect directly to several other sequences in the OEIS.
Like A069834, A213671.
Hold on.
Exactly. A236999, A125650. It just shows how interconnected these things are. A000265 isn't just isolated. It's like a building block that appears in many different mathematical molecules.
It really drives home that OEIS web of connections. So, okay, beyond these cool structures, what about its core mathematical properties? What makes number theorists particularly interested in A000265?
Well, one absolutely crucial property is that it's a multiplicative sequence.
Multiplicative. Okay, what does that mean practically?
It means that if you take two numbers, n and m, that are relatively prime, meaning they don't share any common factors other than 1.
Like 3 and 5.
Perfect example. Then the odd part of their product, a n m, is simply the product of their individual odd parts, a n times a m.
So A35, which is A15, should be A3, A5.
Let's check. A3 is 3, A5 is 5, so A3, A5 is 3, 5 is 3, 5 is 15.
And A15. Well, 15 is already odd, so its odd part is just 15. It works.
It does. This property is incredibly useful. It lets you figure out a n for large n by breaking it down into its prime factors.
Ah, very handy.
And it goes even deeper. It's what's called a strong divisibility sequence.
Strong divisibility. Okay, that sounds impressive.
It is. It means something quite profound. The greatest common divisor GCD of any two terms, say an and am, is equal to the term corresponding to the GCD of their indices. So GCD am, an, am.
Wow. That links the values in the sequence back to the relationships between the input numbers in a really tight way.
Exactly. It shows a remarkable internal order. And a consequence of that is it's also a divisibility sequence, meaning if n divides m, then am must divide am.
So like 3 divides 6, we saw a 3, 3, and a 6, 3, and 3 divides 3, or 4 divides 12, A4, 1, A12, 3, and 1 divides 3 at whole.
Just precisely. There's this hierarchical structure, and it's even simpler in a way. It's completely multiplicative if we handle the prime 2 especially.
How so?
We know A2, 1. And for any odd prime p, like 3, 5, 7, 11, AP is just p itself. Since it's multiplicative, with that caveat about relative primality, which works fine for distinct primes, you can find an for any n just by knowing its prime factorization and applying these rules.
So, like for A12, 12 is 22, 3, A12 should be A22, A3, we know A4 is 1, and A3 is 3. So 1, 3 is 3. It really works like building blocks.
That's the power of it.
Amazing. And you mentioned earlier how the operation itself feels intuitive. Does it have a neat recursive formula, too?
It absolutely does, and it's very elegant because it directly mirrors the remove factors of 2 process. The formula is an. If n is odd, then n else an2.
Ah, so simple. If it's odd, you're done. If it's even, just try again with half the number.
Exactly. Let's trace A12 again using that. 12 is even, so we calculate A122 equals A6.
Okay, 6 is even.
So we calculate A62, A3.
30 is odd.
So we stop. The result is 3. The recursion unwinds perfectly until it hits that largest odd divisor.
That's really neat. Are there other ways to express it, maybe more computationally?
Yes, there's a direct formula, AN, N2V2N, where V2N is the two-adic valuation of N, basically the highest power of 2 that divides N.
Okay, so find the biggest power of 2 that goes into n and divide n by that.
That's it. It's the same result, just phrased differently. And connecting it to, the wider world of number theory, it even relates to Euler's totient function, phi.
Really? Phi? How?
It turns out that AN is equal to the sum of phi for all odd divisors d of n.
Wow. So it pulls together concepts about divisors and relative primality.
It really does. It shows how deeply embedded it is. And for the analysts out there, it has well-defined generating functions.
Ah, the ordinary generating function,
Yeah.
OGF, and Dirichlet generating function.
Exactly. These are like compact mathematical fingerprints for the sequence. They encode all its terms and allow for powerful analysis, connecting it to things like the Riemann-Zeta function and other important series. It signals its importance in analytical number theory.
So we've seen the definition, the cool structures, the core math properties. Let's bring it back. Why should someone, maybe a number theory student listening, really care about A000265? What's the payoff beyond it being, a neat puzzle?
That's the key question, isn't it? Its importance comes from its surprising ubiquity. It pops up in areas that seem, on the surface, totally unrelated.
Like what?
Well, for instance, it appears when you analyze the numerators and denominators of the Taylor series expansion for the tangent function, tan x.
Seriously, tangent. How does the odd part of n get involved there?
It's intricate, but it emerges from the structure of the coefficients. It also shows up quite directly in simple expressions. It's the denominator of 2nn when that fraction is reduced, and the numerator of n2 and a1.
Those seem fundamental.
They are. And if you browse resources like Eric Weistand's Math World, you'll see A000265 mentioned in articles on trigonometry angles and even something called sphere line picking.
Sphere line picking, geometry again.
Exactly. It shows how this very basic arithmetic operation, isolate the odd part, has echoes in geometric and trigonometric contexts. It's a fundamental building block.
It really underscores how simple rules can build complex systems.
Precisely. And from a practical computational standpoint, it's also very efficient to calculate. Programmers might use bit shifting, like n valuation n2, or a simple loop, while n is even, n equals n2. It's algorithmically nice.
So it's elegant, fundamental, surprisingly connected, and efficient to compute.
You've summarized it perfectly.
What a fantastic exploration this has been. We started with just remove the factors of 2, which sounds so basic. And we found this sequence with fractal qualities, these elegant tabular and triangular forms, powerful rules like multiplicativity, and connections reaching into analysis, trigonometry, even geometry.
Yeah.
A000265 really is the perfect embodiment of the odd part or largest odd divisor, but it's so much more than just that label suggests.
It truly is, and it kind of leaves you with a thought, doesn't it? Well, this whole rich structure came from just one simple operation, filtering out powers of 2. It makes you wonder, what other simple filters or operations on integers could be hiding similarly deep and interconnected mathematical landscapes?
That's a great point. Like, what if we removed all factors of 3? Or looked at the square free part?
Exactly. How many other fundamental ways of looking at numbers are there that reveal unexpected structures and connections? This sequence, A000265, shows the potential payoff of such explorations. Removing powers of 2 connected arithmetic to geometry and analysis, what might other removals connect?
That's a really provocative thought to end on. A great challenge for anyone listening. Maybe start by exploring the OEIS yourself.
Absolutely. A000265 is a fantastic entry point, and check out its cross-references. It's a gateway to so much more.
Definitely. Well, thank you for this fascinating deep dive today. And to our listeners, until next time, keep exploring those numbers.